Hi, everyone. Welcome to the webinar. This is How to Scale Physical AI, applying foundation models across upstream oil and gas operations. I'm Cecilio Baldus. I'm head of solutions engineering here at Archetype AI. I'm joined today by Lucas Giannini, also on the solutions team. He's a AI solutions specialist. We've all seen how AI has transformed our lives and work over the past few years, particularly large language models. And they fundamentally changed how we work in the digital world with text and with images. And whether or not you're generating software code or summarizing text, generating uh, some notes. These tools compress the amount of time it takes to do these tasks from, days into hours. And the underlying technology is a foundation model, and it's based on the premise that if you have a large enough neural network developed in a certain architecture, and you train it on a world of books and articles and research papers, and text, what it does is it starts to have these emergent capabilities, and it's able to generalize across tasks and domains. And whereas very recently we were only able to do things like simple semantic analysis, where you would feed in a lot of sentences, and a person would go in there and rate it as a positive a sentiment or a negative sentiment. Now these we are able to generalize that specific use case of sentiment analysis along with anything else that comes out that you can naturally do with language. These are these emergent capabilities. But while we've seen this migration, this AI transformation in the text world, in the physical world, and in robotics and beyond, into factories and warehouses and assets that run in the field, and oil and gas specifically relevant to this webinar today, we've yet to have this real AI moment. Um, and this is and if you look at the impact, these assets, these economies, these factories, warehouses, manufacturing runs our basic global economy. The impact on these devices, the failures of this infrastructure has significant impact to our society, productivity, and our economics. Um, and yet, LLMs, large language models, have dominated the conversation, but they've never really been designed for the physical world. They were designed to handle text, and they were designed to handle code. But the physical world doesn't communicate in words and code. It talks in terms of torque and pressure and voltages and vibrations. The physical world generates an enormous amount of complex data. It's unstructured, it's messy, it's noisy, and it shifts over time. And the challenges today come in a couple of camps. If you look at where industrial sensing is today, it's in the world of bespoke models. We're using a lot of traditional analytics, calculus, and machine learning, where we're trained in a very narrow domain. We have models that are pretty good at a very narrow task with a very well-defined sensor, um, from a specific vendor, and operating in a specific set of ranges. And then on the other hand, we have LLMs. And despite their really impressive capabilities in the world of text, they were not built at all to handle the world of physical AI. We need a paradigm shift here to be able to process these physical signals and to be able to generalize in the physical world, the same way that we've been able to achieve this with text. If you look at oil and gas, for example, there's a lot of dynamics happening, right? You have a few different things. You have the well itself, and when you look at the well is sitting on top of a geologic formation of different types of rocks. These rocks all have different types of characteristics to them, porosity, permeability, and then they have different types of fluids and fluid mixtures, gas content. There's water mixed in there. And that's just the physical characteristics of where you're drilling and pumping. Then you have the actual rigs, the machines sitting on top of there, the drills, the pumps, the compressors, different types of configurations, different types of sensor packages. As you're laying down a drill, it's getting longer. The dynamics of it are changing. And then you actually have the changing conditions into which you are drilling into. As you are drilling over time in a specific spot, the pressures are changing, the fluid composition is changing. There's dynamics affecting the operation of this across the board. Um, and if you look at, again, how we traditionally and how we solve this today traditionally is very, as we say, a very bespoke way. It's kind of a one-off solution for a specific sensor package for a specific use case and a very narrow operating condition. And you'll look at, here's a typical, this is how we would, develop a model and try to deploy. We'd collect an enormous amount of data, then we'd engineer this data, we'd do some pre-processing on it, we'd clean it up. We may have to go through a lot of labeling. We go through a training phase. We train this model, and then we do some evaluation on past data sets, and then we actually go to deploy it. Hopefully it works out in the field. A lot of times it doesn't. You're going to have to go back and do some additional work. And even if it does work, what you'll find is because of all those different problems with drift, and drift again being the deviation of a set of conditions from where it started. Um, again being the geology, the machine condition, the age of the machine, the state it's at in the operation. You might actually have to go back and continue to retrain it. So you're constantly chasing this problem, and it's very expensive. It's expensive to deploy it, and then it's expensive to maintain it. And that's the model capabilities itself. But if you look at the operational, the setting where you're working, we're very used to having access to a cloud all the time. Anytime we're doing any text processing, and our chatbots are connecting to a large data center somewhere. In the field, we may or may not have a steady connection to the cloud. And further than that, when you're interacting with a chatbot, you send a little amount of text, it goes off, it does a process, and it sends you a little bit of text in response. When you're working in the physical world, you are dealing with an enormous amount of data. We talk about data gravity being that the amount of data takes a lot to move it around, and it can be very expensive as well. So where you run your inference, where you run your intelligence, matters. You may not have the luxury to run it on the cloud. You may need to run it directly on the device, sitting at the device in a small box over there. So Newton is our foundation model. This is it's here to solve the problems that I talked about. This is Archetype's foundation model, and the problem it solves is a singular model that allows you to scale across different sensor packages, across different use cases, across different operating situations. It's trained on an enormous amount of data, and I said before, a large enough neural network in a specific architecture with an enormous amount of data, and it understands the data of the physical world, the messiness of it, the missing data. It understands all types of different physical data. At the end of the day, if you think about the physical world as a superposition of sine waves, effectively, that's the language that it speaks in a statistical way. So it doesn't have, a lot of times I hear, does it work with this particular brand of sensor? If your sensor is the type of sensor that senses the real world, a physical phenomenon, it speaks that language. Beyond the model itself is we have the archetype platform. So the platform manages more of the AI lifecycle. This is from running inference, from training. A lot of what we're finding is that our use cases are solved a lot of times directly out of the box and without any changes. But in a lot of industries, you might want to fine tune it to really optimize the accuracy of your domain. So, the platform allows you to fine tune it depending on the target of where you want to deploy it. If you want to deploy it on a cloud or on an edge or right directly on a small box on an asset, you might have to distill this down into something that's more manageable. This is part of what our platform provides you, from cloud to edge. And we are not in the business of managing infrastructure. What we do is provide you a set of capabilities that allow you to own that within your own security perimeter. Your data never comes to us. Your data is important to you. Your businesses are rely on them. That is completely kept within your security perimeter. And any models that you fine tune, any models that you distill also remain part of your library. They never come to us. They never get integrated back into the foundation model that your competitors would be using. So what you have is a universal foundation model that has this ability to locally adapt. So that allows you to deploy faster, and that allows you to adapt to drift and those changes that I talked about earlier, a few slides back, to do with the specific geology that you're working in, the fact that your assets are aging, that there are different configurations, that you have different sensor fleet packages on them. And then over the course of your operation, when you start pulling oil out of a well, there's going to be a different pressure characteristic, different fluid characteristics than, a quarter into it, halfway, and more depleted. And then it gives you the opportunity to interact with humans, to pull intelligence out of that, or to make it part of your operations in an automated way at the time that you feel comfortable with this. If we look at what this looks like, in the language of our model, these are our plots of what we call our embedding space. This is the world that it understands. So we take raw physical data, it gets encoded into this embedding space, and what we do is this high dimensional space. It's kind of what humans think in. We think in a high dimensional space. We can't really see high dimensional spaces, so we flatten this into something that's represented here on a that we can look at on a slide. And if you look at like a motor or an industrial pump or an oil rig, what the model has done is over the course of a lot of runs, it's showing you that the data naturally clusters in this embedding space on its own. So it is natively understanding, because of its past experience with an enormous amount of data. It's able to cluster. There's these natural clustering phenomena that happen. But here is a physical clustering of data in the embedding space. Now you want to add meaning to it. Those physical things, such as a blocked intake versus, gas interference, those are semantic human words that we're putting onto a physical phenomenon. So what you can then do is you can pair your domain knowledge with the clusters that exist, so that you can actually represent these and into something that's actually actionable by your operators or by another machine. Um, Beyond our foundation model and the platform with all of the capabilities to manage the life cycle, we're also building agents. And agents are a higher level of abstraction that allow you to do a certain set of tasks, extract certain types of intelligence out of our foundation model in a more turnkey way. And whether or not we're talking about operational state monitoring, where you're trying to classify different types of operational states like blocked intake or gas interference, or whether or not you're working in the video field with task verification. I don't want to go into these too deep. If I please encourage everyone to look on our website. We just released a lot of material and posts about all of these different types of agents. Please go to our website to take a look. Specifically, if you're looking at how to use these agents in general for, upstream operations such as drilling or producing, what you're looking at is optimizing your operations in a few different ways. You want to optimize your equipment, and you want to optimize the process, right? So the machines, if when there's failure on these machines, it's an enormous cost. The downtime is enormously expensive. It can be quite dangerous as well so it impacts the safety of your people. There's also invisible lost time, so inefficiencies in the equipment and how it's being run are based on the current conditions of what's going on. So and you don't want to be to have your wells producing below their possible capabilities. So using Newton and using the agents on top of that, what we can do is apply different types of agents to help you in that for drilling optimization as well as pump optimization. And what that looks like, for example, from the machine side, optimizing the operational state or looking for anomalies or rare event detection. You can optimize the health of your assets. You can optimize your maintenance cycles. You can get in front of catastrophic failures. And then on the other hand, from an operational perspective, this is about optimizing with the single asset, the single rig that you have. How do you optimize and extract the most amount of product that you can so that you're using the tech that you have deployed in the most optimal way? And just before I hand it over to Lucas, I want to say this is an area that we're working with a number of clients in this space. The problems are real. We're in the process of delivering solutions. And this example here is built on some open source drilling data, but the what we're providing our clients is the ability to deploy these solutions and their assets faster, maintain them at a lower cost, and really extend the life of their rig and maximize the operations at every site using again a common foundation model using and then on top of the Archetype platform. Yeah, thanks. I'm going to pass it over to Lucas now.
So I think we discussed this slide previously. We just wanted to bring it back to basically highlight how complex and time consuming it is to build and maintain classical ML pipelines, right? So you of course need to start by having a significant amount of data and it of course needs to be labeled. Then you go through the whole process of feature engineering and data processing to be able to finally train the model. You of course need to evaluate it, right? Make sure it actually works. You deploy it, and then depending on your conditions, right? If your conditions are changing significantly over time, you're probably going to have to retrain it in, I don't know, a couple of months. So those traditional pipelines are definitely not simple, right? They're complex and they are time consuming. And we also highlighted here the steps which can be quite critical, right? If you don't have extensive data and this data is not labeled, then you won't be able to train a ML model from scratch, right? So this is not trivial. This is not a trivial process for sure. Now this changes significantly with Newton, right? With our foundational model. So first of all, Newton was already pre-trained on billions of data points. So this entire pipeline changes significantly. First of all, those critical steps that we mentioned, they are not critical anymore because you actually need a much smaller sample of label data to make the pipeline work. So this is what we're calling the end-shot examples. We'll be discussing this a little bit later, but normally when you have 10 of those, it's the rule of thumb that we normally use, it's already enough to go through the pipeline. And by the way, this pipeline is not about, retraining a model. As I said, Newton was already pre-trained on billions of data points. It's actually changing a couple of parameters on this new inference pipeline. And those parameters are something like the window size, the step size, or there's some kind of smoothing that we need to do in the data. But it's pretty straightforward, and you are already able to get some inferences out of it. You, of course, need to evaluate it and deploy, but every time that you need to retrain, as I said, it's not about, training an ML model from scratch. We are using the foundational model, changing a set of parameters, and maybe providing some more recent end-shot examples. So it's definitely simpler, right? Now, just highlighting briefly what we just discussed, right? It works with limited label data. You don't need to go through the feature engineering process. It also generalizes well across assets and wells, right, in general. And it adapts to recent changing conditions, right? I think we covered most of those topics. And And we've been using a lot these terms like zero-shot learning or few-shot learning. I think now we're just bringing this to the framework. I think it's important to mention. When we're talking about zero-shot learning, it means it's actually the situations where no labeled data is required, right? As I said before, Newton was already pre-trained on a very significant amount of data. So it's actually possible to extract some insights from it, some insights from data, even though it's not labeled, right? Normally, when you want to identify an anomaly or some kind of unknown state right out of the box, Newton, even though you don't have labeled data, can already do a good job at it. Now, if you do have some data, some samples of specific states or events that you want to identify in a new set of data, that's when we can go to the few-shot learning framework, right? So basically provide those examples to Newton. It understands the patterns on it, and whenever you want to classify new data, it will use, of course, the foundational model itself, but it also use those examples that were provided to classify, as I said, some states or events. Now, there's also a third option here, which is fine-tuning, and this is different than the other ones, right? This is when you want Newton to learn a new and extremely complex behavior, right? You're literally going to change the weights of the model, so it requires a lot of samples, and of course, those need to be set to be labeled as well. So this is a way more complex scenario, and the reason for that is because it's a way more complex use case, right? We want Newton to learn a very complex behavior for that, and that's normally when fine-tuning goes. One thing that it's also important to mention when we are handling those when we're working with n-shot examples, right, is that we can scale this across many different assets, right? So the bare bone, the foundational model, is all the same, and given the fact that we are basically providing it new shot examples, we can use those n-shot examples across different assets, right? So that's very scalable across different assets. One example here is if it's the case, for example, that we have a set of wells, and we only have, for example, data available from, let's say, well 1, well 2, and well 3, and we're extracting the n-shot examples from those, we can actually run inferences on well 4 or well 5, given that the foundational model is the same, and we're using those n-shot examples from other wells, right? So I think the core message here is that we can easily scale that and deploy that across different assets with this few-shot learning logic, which is pretty powerful. I think we're getting close to the demo part now. I think we brought this slide basically to demonstrate the demo before in a static way. On the left-hand side, we have raw data, right? And we're going to see raw data as well during the demo. Once we send this raw data to Newton, the first thing that it does is it maps each one of these data points to a specific region in its embedding space. And we're actually going to be able to see this also very well in the demo itself. But essentially, those regions, they correspond to specific behaviors of the sensor data, right? And then one important thing, one very cool thing that we can do is actually map each one of those regions to a specific state that we are aware of, right? And we'll be doing this with the n-shot examples that we have, and we're going to show this in a second. Now let me just move back here to the demo. I'm actually going to name it, let's call it rig state identification. This is how I want to call this specific agent that we built right now. And the first thing that I'm going to do is add this operation file, right? So operation file here is literally the file in which we want to run the inferences on top. So we want Newton, we want this agent that we are creating here to be able to identify specific states on this operation file, right? I can actually click here to see how it goes, and you see that this is classical time series data, right? Referring to that specific oil rig operation. Another thing that I mentioned previously was that the new pipeline essentially becomes tweaking some parameters, right? We can see some of those parameters available here. I'm not going to go into details, but it's significantly simpler than going through the whole feature engineering and training part, right? Now that we have our data, I'm actually gonna hit the adapt button already. And what's happening here is the part that we showed in the previous slide, which is we're sending some samples, right? Some windows of this time series data to Newton. We're getting an embedding out of it, right? Which essentially, represents the behavior of those specific windows. And now we are running some dimensionality reduction techniques to be able to plot this in the 2D world, right? So essentially, each one of those dots that we're seeing on the screen is a window that was used as an input to get an embedding out of Newton, and then this embedding, of course, is high dimensional, but we're applying some dimensionality reduction techniques here to be able to see this. You see that we have overall 78 in those windows, right? We are 40 at this point, and so let's just give it a couple of minutes, and we'll have the embeddings in a second, all the embeddings in a second. Okay, we're almost there. One thing that we can already start seeing is that Newton clusterizes those data points in specific regions of the embedding space, right? I think, yeah, nice. That looks pretty nice, actually. So we see that there are 3 clear clusters in the embedding space, which were generated from the sensor data, right? And the big thing here is that we don't know what those mean. What Newton understood was that those data points here, they behave differently from those data points, and they behave differently from those data points. So they got clustered in different regions of the embedding space. We actually don't know what those mean. One thing that we can do is actually look at how those states vary, or how they transition, right? How the time series transitions across those different states. But again, I don't know what they mean, and Newton also doesn't know at this point what they mean. That's why they call it state A, B, and C. Now, what we can do now is add those labeled examples, right? So imagine that we can extract from historical data a specific time or period in which the time series corresponds to a drilling state. And you see that here it's pretty similar, right? The same features that we had previously, but we know that those features now represent a drilling state. I'm gonna hit the adapt button now. You see that we have now 15 windows to generate. We'll start sending those windows to Newton, getting the embeddings back, and then plotting them in the same embedding space that we created previously, that we calibrated previously. Nice. That's actually pretty nice. So we see that drilling state matches very well to our state C, right, that we got previously. So there's a very, very high chance that those state C that we initially discovered is actually a drilling state, right? That's how we can, generate inferences and classifications in real time with Newton. Let me add those other 2. So as I said, we have historical data on when the trip slips and when the drill it's not hitting the bottom. Those 2 states we can also provide as end-chart examples. I'm gonna hit the adapt button again. Now we have 30 windows, so it's probably gonna take a little bit longer. Nice. We can see that the when the trip slips, it matches here our state A. Okay, we got all of them. So trip slips matches state A, and then off bottom matches here our off bottom state, right? So I think this is basically what we wanted to cover. The core messages here are we essentially provided a file in which we wanted to run inferences on top. We also and actually, even before we shared the end-chart examples, Newton was already able to identify some existing states, right? The thing is, we didn't know what they were. So after we provided nchar examples, we were able to map each one of these discovered states to our known states, right? And that's the part where it got pretty interesting. And all of that, of course, without having to do any kind of work in terms of feature engineering or processing. We basically define a set of parameters here, and the pipeline ran.